You know, graph neural networks can feel like total magic, but what if I told you they're built on an idea that's as simple as a drop of ink spreading in water? Well, in this explainer, we're going to unravel GNNs right from the ground up, starting with that very first principle. Let's dive in.
I want you to think about the weather for a second. A thermometer might say it's 20 degrees Celsius, but if it's super windy and cloudy outside, it feels a whole lot colder, right? That's because that number, 20, doesn't exist in a vacuum. It's shaped by its context. And that simple, powerful idea is really at the heart of all graph learning.
So here's the big question. How do we actually build a system that lets our data talk to its neighbors? I mean, how do we create a mathematical channel for that wind and that cloud to influence the reading on the thermometer? That's the exact challenge that GNNs were born to solve.
To answer that, let's start with the most intuitive way information could possibly spread. It's a process called diffusion. And trust me, you've seen this 1,000 times. Just picture a single drop of ink slowly spreading out in a glass of water.
The engine that drives this whole diffusion process is something called the random walk operator. You can see it here as P. Now, don't worry about the math just yet. A is basically a map of who's connected to whom. That's the adjacency matrix. And D, that just counts how many connections each node has, what we call its degree. Put them together, and they create a super simple instruction for every node on the graph. Replace your current value with the average of your neighbor's values. That's it. It's a pure averaging machine.
So what does one step of this averaging process actually look like? It's pretty straightforward. First, a node looks at all of its neighbors and just sums up their values. That's the aggregate step. Then, to get the average, it simply divides that sum by the number of neighbors it has, its degree. And boom, that's it. That's one tick of the diffusion clock.
You know, averaging seems like a perfectly fair, kind of democratic way to share information and decide on a collective opinion, doesn't it? But this seemingly harmless process, well, it has a dark side. Let's see what happens when we let it run on a loop.
Let's watch this play out on a really simple path graph. Imagine node 1 is very positive with a value of 1, node 3 is very negative at -1, and node 2 is just sitting there perfectly neutral at 0. There's a lot of tension here, a lot of disagreement in this initial signal.
And look at that. In just one single step of averaging, all that interesting tension is completely gone. Every single node is now 0. The positive, the negative, the neutral, it's all been wiped out, flattened into one uninformative value. The signal has totally collapsed.
A perfect analogy for this is just mixing paint, right? If you start with distinct colors, like a vibrant yellow and a deep blue, and you keep mixing them together, you don't preserve the original shades, you just end up with a uniform green. The individual identities are totally lost.
And don't think this is just some fluke of our simple little example. Oh no, it's a mathematical guarantee. This process, which we call oversmoothing, is the inevitable fate of repeated averaging. It doesn't matter how colorful and varied your data is at the start, if you just keep mixing, you will always end up with a uniform, boring, uninteresting gray. But this collapse isn't just about losing information. It happens for a very specific reason. If we look closer at this whole averaging process, we find a hidden bias, a fundamental unfairness in how it decides which nodes get to have the most authority.
So here's the problem. Nodes with tons of connections, what we call hubs, they have all the power. In this averaging game, their role is like a heavyweight on a seesaw. Their opinion just completely flattens the voice of the smaller, less connected leaf nodes. It's not a fair conversation at all. Okay, so how do we fix this? How do we fix this unfairness and balance the authority in the network? Well, the answer isn't to stop averaging, but to change our geometric perspective with a really clever trick called normalization.
The tool that fixes this problem is called the symmetric normalized Laplacian. Now, I know the formula looks a little intimidating, but the idea behind it is actually quite simple. It's designed to rebalance the conversation. It essentially says, okay, you're a big hub with 100 connections, so I'm going to divide your influence by a factor related to that 100. It's kind of like a way of handicapping the powerful nodes just to give everyone a fairer say.
All right, this right here is the core insight of the whole geometric fix, and you can see it right there in the equation. We stop comparing the raw values between nodes. Instead, we first scale each node's value by a factor related to its degree, and then we compare them. It's like putting the heavyweight and the lightweight on different spots on the seesaw to balance it out. This one simple change completely redefines what disagreement means and brings balance back to the whole system.
And this rebalancing has a really fascinating effect. It makes the big hubs stiff. Their values become much harder to change. They basically turn into stable anchors for the entire network. And at the same time, it shields the little leaf nodes, making sure their unique signals aren't just drowned out by their noisy, powerful neighbors.
So this geometric fix is really powerful, but it's still a fixed, one-size-fits-all rule. What if the network could actually learn the best way to balance authority for whatever specific task we're trying to solve? Well, that's the leap that takes us from a fixed process to the flexible world of graph neural networks.
Here's the thing. These classical spectral methods are slow, they're rigid, and frankly, they're a bit dumb. They're computationally expensive, which means they just don't work for massive real-world graphs. They're not local, so if you add one new user to a social network, you have to recalculate the whole thing from scratch. And they're task agnostic. They only see the graph structure, not the specific problem you actually care about solving.
This next slide shows the brilliant pivot that made modern GNNs possible. See, the old methods tried to understand the whole graph at once, a really slow global process. The new idea was to forget all that and just go local. So instead of one giant calculation, we do a series of small ones. As you can see in the diagram, we start by just looking at our immediate neighbors. That's one hop. Then we look at their neighbors, 2 hops, and we just keep going. We build up a picture of the graph by exploring these expanding local neighborhoods, which is just way more efficient.
And all of this brings us right here to the modern GNL layer. This is the ultimate evolution of our simple ink drop idea. It's local, just like our approximation. It's fair, using the principles of normalization we just talked about. But here's the magic. Instead of using a fixed rule for how information spreads, the GNN learns the best set of rules to solve a specific problem. It's a smart, adaptable, and incredibly powerful version of that original diffusion process.
So let's just recap our journey real quick. We started with the really intuitive idea of diffusion. We saw how its simple averaging rule leads to oversmoothing and collapse, all because it gives way too much authority to those high-degree hubs. We fixed that unfairness with geometric normalization, and finally, we made the whole process local, efficient, and learnable. And that right there is the conceptual path to the modern GNN.
This whole journey really helps us bust some common myths. First off, oversmoothing isn't a bug. It's the natural behavior that GNNs have to learn to control. Second, GNNs aren't some radical break from the past. They're the smart, operational continuation of spectral theory. And finally, normalization isn't just some minor tweak. It's a fundamental choice about how we define fairness and authority on a graph.
So we're left with this really fascinating final thought. We started with a natural process, diffusion, and we built a learning machine that could actually control it. So what's next? What other complex processes from physics or chemistry or biology could we teach an AI to understand and direct? The possibilities are just incredible to think about.